Okay, what's the SPD notation for nitrogen? Let's look at atomic number. You need to know its atomic number. Then you fill the electrons into the orbitals, isn't it? So what is the atomic number of nitrogen? 7. Okay, so if I want to do the SPD notation, what do I do? 1 S, how much? 2. Then what do I do? 2S, 2. Then 2P, how much? 3, isn't it? So if I wanted to show this in box notation, I show my electrons with an opposite spin, isn't it? Because electrons repel each other, so they don't spin in the same direction, isn't it? Then above, I do the same. I have 2 electrons in the S. Then for the P, I have to show the 3 P orbitals. Your PX, PY, and PZ. In this case, I have to fill them singly first. And then you pay them up later. So you're not allowed to pay them up before doing this. Those are by O-level, by Mutstanga, one just also pay later. That was basically the idea. Right. There are some unique properties of transition elements, and what did we say? Do you still remember what we said about my SPDF notation? We commented on SPDF notations of transition elements. What example did we use? Chromium. Now you can check with your notes if you have them. What was the comment on the behavior of these transition elements? It's a topic on its own. So when he shows us this, we move on to the next thing that we talked about. I'm going to skip other things around. I'm going to skip. After this, what did we talk about? We talked about ionization energy, isn't it?
Yes.
And we said, what is ionization energy? There's a standard definition for ionization energy. There's a general definition, which is to just say the amount of energy needed to what, in general, to remove electrons. But what is the standard definition? Because it's energy, it's going to be measured in what? What are the units of measuring ionization energy? Kilojoules per mole, right? Per mole. So there has to be a standard definition. So what is it? How do you define ionization energy? Yes.
Amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form monopositive ions.
Correct. So you have to acknowledge that we are dealing with 1 mole of gaseous atoms to form 1 mole of gaseous ions. That would be your first ionization energy. We talked about successive ionization energies. You can remove the second electron, in which case it's called the second ionization energy. It's supposed to be discussed even later on when we do transition elements. Right. Let's skip to something. Mass spectrometry. When we say mass, no. What is the general formula for calculating the mass of isotopes? So you are given a sample of an element, it's put into a machine. What happens? There are a lot of things that happen, but you have your monopositively charged ions which are detected by the machine. So if you take a sample, it's going to have some isotopes. Take a sample from the natural world, you analyze it, you're going to find some isotopes. So there's something called percentage abundance. Abundance of the isotope. And the isotopes will also come with what? With different masses or M&D ratios, So there's a general formula everyone must know to calculate the average atomic mass of an element from the average masses, isotopic masses. from the average isotopic masses. And okay, so let's pass on it. From there, we talked about you can also analyze simple molecules such as banana chlorine. You can put a chlorine sample into this mass spectrometer. And one of the common questions is how many peaks are you going to find on the graph? What's the idea here? This one will what? It will change to this Cl2 plus. And then is united, guys, in the spectrometer. Now, what you have to think are the possible combinations of the chlorine isotopes. So it's my isotopes so you can analyze simple molecules such as chlorine or oxygen. Oxygen, that's the same these diatomic molecules, simple molecules. So you also want to check my graph simple molecules. You can also analyze my organic molecules. So organic molecules, what they do is that they split when they, for example, let's just pick just to illustrate. If this organic molecule is put into a spectrometer and it would split because of the processes that occur inside the spectrometer. So you might have, it might split here, for example, in which case it forms a C. It forms this ion. So if this ion falls onto the detector, a mass corresponding to this will also show on your peaks. And it might split here, in which case you have this also showing. And so organic molecules, what they do is they split because of that bombardment with high energy electrons, etc. And so zikadaro tikuti isusu, your best estimate would be the highest M&D ratio. The highest mass that you get would be your best estimate. And what did you say? What's the statement? The major peak at the what? At the highest M&D ratio. Just that. Where would be not to split this molecule like we did here? We had a positive charge without splitting this molecule. And so we are saying we should have a molecule like this with a positive charge that can be detected. So that's our bet that the highest, the major peak and the highest M&D ratio is the estimation of the MR of that compound. And that's the logic behind that. So major peak and the highest abundance at the highest M&D ratio. So we also looked at that. So you can check other examples of molecules or ethanol or guys come on spectrometer to see what are the peaks. Guys, so I want you to randomly pick any topic that we did to discuss. Let's have some questions, because following through everything, we covered a lot. That's what I used to do. Even if you want to take us to the last topic we did, it's fine. Let's just go through a place where you feel like you need clarification. And then after this, we can also do you have this? We can try to pick a question per topic in English by you. So, each. But I have the topic, let's try to look for it and it will move on. Then you have a question. So let's get to something that you're curious about. Something that you feel like bad. And also to say it's going to make sense. So